All right, good morning. Welcome back to ENHS793. We're going to talk a little bit today about soil formation factors, a little bit about the four major processes of soil formation as well, and then go on, based on that knowledge that we gain, talk a little bit about soil horizons. I'll probably do soil horizons in a separate video clip based on the PowerPoint slides I have. They were fairly good, and I felt that it wasn't really necessary to do any to go without them. So I'm just incorporating them into this talk right now, and I've got my whiteboard behind me in case I need to explain anything to you. There's a guy, a soil scientist. I think he was born in Switzerland, and he ended up, if I'm not mistaken, at UC Berkeley. His name was Hans Jenny, and he postulated and later also showed that soil formation was a function of climate, parent material, organisms being fauna and flora, relief, and then of course time. So that was Hans Jenny's great legacy. He left a lot of legacies, and really it was a great way to look at soils and soil formation, because the result is this ordered arrangement of sand, salt, and clays, organic materials, colors, and you'll see that in the layers of soil that we can see outside in the field. Soil is rarely, if undisturbed, is really homogeneous. You've always got these kind of layers and little mottles and things like that. So I think Jenny was a soil genius, and we'll be able to see some of these things in the process. But the kinds of horizons and properties they impart separate one kind of soil type from another. So based on that, you would not expect to see a soil type that you find, say, in North Dakota to one that you would find in, say, Uganda. Very, very different, even if they have similar things like geology. But let's go ahead and have a look at that. The first thing that we'll touch on, it's by the way, if you go back and look at it, the acronym, the acronym for this way of looking at soil formation we call CLORPT, C-L-O-R-P-T. So just keep that in mind. So let's go to parent material rather than climate first, and then we can go back to climate. But parent material is basically the state of the soil system at time equals 0. So the parent material is going to be what's the underlying material. So that's very much a geologist's kind of question. Is it granite? Is it some kind of metamorphic rock? Is it some kind of sand? Has it been deposited by water? Has it been deposited by wind? If we have a look at that now, your parent material is really going to be one of the major things that contributes to the mineral component. Remember, we've got the four components of soil is mineral, organic material, air, and water. So the mineral component is a vital component, and the underlying soil, at least the underlying geology, parent material is very much the important part. This kind of thing shows you that kind of how development of a soil would come from bedrock, and it starts with the bedrock, and the rock disintegrates. Little bits of organic matter, mosses, lichens, and that kind of thing gain a foothold, and then you've got shrinking and swelling through the freezing and thawing processes. You've got you've got water beginning to penetrate down, and as that happens, more organic matter begins to take hold. The roots then go down, and then you have these formations. First of all, what is known as the A horizon, and then later on the B horizon, and then later on the C horizon as well. That we'll cover towards the end of this talk or in the next one. But through this process of weathering and other processes, you'll find that different separate layers form from that basic bedrock that has come out. What kind of parent materials do we find? Well, you've got the glacial till. We don't really have much of that around here, but it's moved by glaciers from one place to another, and you'll find that in, for instance, the northern part of this country. Loess is found in a number of different places, but probably the most prominent would be in China, where you've got or it's actually not. Some people call it Loess or Luss, pronounced Luss, the Luss Plains, and that was at one time an extremely fertile part of the world. Very, very deep sandy soils, wind-blown soils. Alluvium is soil that was deposited by water, and you'll find those often in valleys, and they're often fertile soils. Colluvium is material that has moved down the hill, downhill from, through weathering and through water carrying it, and it's usually at the bottom of a hill. And then residuum would be rock derived things like limestone, shale, sandstone. That's basically in place. We have volcanic ash. Some soils are actually of volcanic origin, and then you've got organic material. In South Carolina, possibly the most prominent example of organic material is, of course, material from the Carolina Bays, where you might have 10 to 20 foot of organic material in the top area. In the Midwest, you also have these the prairie, and the soils are very deep and full of organic material there as well. South Carolina geology, just to kind of illustrate this, South Carolina geology, if you just flip through this, I don't want to obsess about it too much, but the South Carolina geology, the underlying geology over here, really is going to determine or is a big determinant in terms of what you're finding on in the actual soils that you have. And in this northwestern part of South Carolina, above what we talked about the fall line there, you can see Columbia. In this part of South Carolina, we're going to find mainly granite, slate belts, things like that. And these are not metamorphic. These are mainly mostly igneous rock formations. What you'll find just below the slate belt and running sort of in this green area over here is mainly sandy soils, or sand. It was, I believe, deposited either by wind or by water. And then the lower the coastal plain over here is then also sand, but mainly water deposited. So if you look at those and then compare them to the general soils map, you can see there's a remarkable similarity between those. And then, of course, soils then will also affect common resource areas. That's how your natural resources, sand, soil, water, air, plants, animals. Not so much the air, but soil, water, plants, and animals are arranged in these ecoregions. So common resource areas map. So I don't want you to obsess about it, but just illustrating that that the underlying rock formation or parent material plays a huge part in soil formation. And of course, a lot of that was, that kind of thinking was influenced by the soil scientists who had a strong geological background. Just very quickly, we're going to look at the Blue Ridge. That's obviously in the far northwestern corner, mainly metamorphic rocks. Well, I guess not only metamorphic, but also igneous. But granite is, of course, igneous. Gneiss and schist are, as far as I know, metamorphic. I've got a geologist in my class, so I'm going to have to watch my P's and Q's in the geology. But the soils, you'd find a typical soil over here is called an Edneyville, and that is a soil series. We'll talk a little bit about soil series later on, but soils have names. There are about 17,000 different named soil series in the country. But you can see the parent material and the relief in the Blue Ridge are quite unique. If you go down into the Piedmont, you've got igneous and metamorphic rocks again, and you'll get something like a Cecil rock, which is Cecil soil, which has got this very, very red clay in the uplands where you don't have that much moisture. And this Iredell you'll find down in the river valleys in wet parts. So that's a much wetter soil. So this is typical Piedmont rolling plains. You can see over here that tilled soil, which is, most of that topsoil is now gone because of cotton production in the past few years. Just sort of in terms of history, you can see soil erosion was a huge problem over here in the cotton growing period, because people tilled the soil and left it uncovered and unprotected, and you had these incredible gully washes. So you can see the Berry Gully. A lot of the influences on Hugh Hammond Bennett, who started the Soil Conservation Service in the 1930s, he came from this part of the world, and so he saw this kind of erosion firsthand. Whoops, excuse me. So we go down to the sandhills. You can see the sandhills there just below the fall line. Most of the sand is aeolian. Aeolian meaning that it's wind blown. So in a sense, wind blown dunes. Some of them are river deposits. Some of them you will see weathered clays as well. But the thing that characterizes the sandhills is this very sandy soil with very, very low organic matter. For those of you who are unfamiliar with this part of the world, if you go to Sesquicentennial Park, which is just up the road, Sesquicentennial Park is classic in terms of sandhills that you'll find. Okay, you've got the Ailey and the Alpine soils over there. You can see those profiles. Those are beautiful, deep profiles there. We're not going to be able to see too many. Hopefully I'll show you one or two. Your coastal plain, you've got marine deposits and river deposits mainly. Lots of sand, but also loamy soils, deep, well-drained and loamy soils, but quite a bit of sand as well. And something like the Dothan, you can see this reddish color suggests that it's aerated. There's air in the soil profile, whereas this Rains soil suggests that that's in a watered profile. And in the soil formation processes, we'll see how that works out. But yeah, so the Rains is going to be a poorly drained soil. You're going to find that in the lower places. The Dothan is going to be a well-drained soil. You'll find in some of the higher elevations. So that's the coastal plain. Let's go on to climate now. And climate really, we're looking at the role of water and temperature in soil formation. Clearly, if you had very, very cold temperatures where you don't have, for instance, in the North Pole or in the Arctic region where you have a lot of snow, a lot of permafrost, not much is going to go on in terms of organic growth. You don't have that much photosynthesis going on, not much opportunity for trees and plants and roots to form in the soil. Whereas in an extremely warm climate, you have the opportunity for a lot of this organic material to grow and a lot of soil organisms carrying on, which might accelerate certain processes. And then you've got places like the Midwest where you've got a little bit of the best of the both worlds, where a lot of organic matter is going to accumulate. So let's have a look. First of all, in terms of rainfall, there are certain rainfall regions across the world, and that'll be the next slide. But why does water matter? Well, number one, water matters because it dissolves materials that might be soluble, and then when it dissolves those things, it might transport them out of a soil profile. It's also going to the rate of reactions are also going to depend on your temperature and your pH. If your pH is too low or too high, a particular chemical species may not dissolve. Water, of course, is very necessary for plants and organisms. If you had a very high soil temperature but no water, of course, you're not going to have plants growing. And so soil formation factors or soil formation will slow down in that particular case. It transports materials. If it dissolves materials, it'll transport them both internally and externally. So it might transport, say, calcium and magnesium ions right down out of the soil profile that's below 2 meters and into the water table. That would be external. Or it might transport clay from your upper or what is your topsoil into your what is known as your B horizon. The clays would kind of stick there. So it just depends. Water is going to do that transportation. And then, of course, water is also responsible for physically rupturing rocks through freezing and then also the thawing process. And you'll find soil formation processes go on like that. What you find is a few soil moisture regimes over here. We're going to look at these main ones, but you've got aeritic soils, and these are going to be in our part of the world mainly out west, where for 90 days of the year there's not enough moisture available for plant growth, not plant growth, it's plant growth. You've got a Mediterranean climate, which is xeric, and you'll find that, say, in San Francisco, where you've got these cool, moist winters but very warm, dry summers. So moisture is not optimal for plants to grow, for instance, in the summer. So that gives you another moisture regime. Eustic soils, if you go out into, say, Kansas and Oklahoma, those Midwestern, Nebraska, those Midwestern states, you'll find that the soil moisture is, in a sense, intermediate, but tends to be a little bit drier rather than wetter. When you come out to the eastern part of the country, soils are wet for more than 90 days of the year and more than 60 days of the year in summer. And when I mean wet, there's enough moisture in the soil for plant growth. In other words, the plants haven't sucked all of that moisture out of those little pore spaces that we talked about. So that would be a eudic soil. And then per-eudic soil is where rainfall actually exceeds evapotranspiration. and the soil never dries completely. So we don't have that kind of situation over here, but you'll see like places in South America and say the in the equatorial regions of Africa, and perhaps in some of those equatorial Pacific islands, you'll find some of those conditions where it's incredibly moist and everything's basically a wetland. So we've got those soil moisture regimes. Let's look at temperatures. Temperatures are, the higher your temperature, the higher the rate of reaction. There's a law called Hoff's law. I'll just write it down. Not that it's terribly important for you to remember. Hoff's law basically says that for every 10 degrees C increase in temperature, you're going to have a doubling of the rate of reaction, a doubling really of organic activity in terms of organic metabolisms. And I would think that that also applies just to basic chemical reactions. So it's going to influence the rate of reactions in soil. It's going to actually influence the rate of organic matter accumulation in soil. And what does that mean? Well, if temperatures are too high, there are going to be some organisms that feed on that organic matter and basically convert the carbon that is in the organic matter itself and convert that into energy and carbon dioxide. And so you'll have a reduction of organic matter in that soil. The other thing of temperatures, it does influence the heating and cooling of soils. So if it heats the soils above, for instance, the soil is uncovered, if it heats that soil too much, it is going to, you're going to shut down some of those soil organisms. Once that soil temperature is above, say, 105, 110 degrees C, the only organisms that are going to be able to survive, especially in the top 1 or 2 inches, are going to be things like are going to be hypothermic or thermotrophic microbes and organisms. That's not going to be helpful to the majority of organisms. Very cool soils, obviously, once they get too cool, most of your soil organisms are also going to shut down. So I've given you some examples. There's some other examples over here. We've also got microclimates, so we need to remember that, for instance, a north slope versus a south slope is going to be very different, especially in the more northern parts of the country, where a north slope might not see very much sun, very much warmth, and it might look very different. Maybe the best example I can think of is in alpine areas where farming practices, for instance, look very different on the north versus south slopes, and the ecologies are just very different. So again, we've got another world map of soil temperature regimes. I'm not going to go through each one of them, except to say that we are in what is known in the cotton belt. We're in this thermic regime over here. So most of our soil temperatures, our average soil temperatures are between 8 and 15 degrees C. That's our average temperature over the year. The frigid or the mesic soil temperatures we'll find are in this corn belt over here. Just kind of, I'm not going to be too stuck on it, but there are these subtle little differences between pergelic, cryic, and frigid temperatures, and you'll see those differences there. If you want to research that a little bit, you're welcome to do that. And then there's another set of regimes over here. You can see isomesic, isothermic, isohypothermic, etc. When you see that word iso in the context of soil temperature regimes, it means those soil temperatures don't change much from winter to summer. There's less than a 5-degree difference. And of course, in equatorial regions, you typically don't have summers and winters very much, but you would have wet season and dry seasons, at least in the very equator part. Once you get, closer to the tropics, then it looks a little bit different. So, but that's the soil temperature regimes, and imagine now taking soil temperature regimes and the soil moisture regimes and laying them over one another. You can immediately see, and then laying over that the soil geology, you can immediately see that you're going to have a lot of influences on what kind of soils you're going to find in a particular place. When we talk about relief, we're really talking about not only elevation, but inequalities in the land surface that you're going to experience. And you want to consider those things collectively. So you're thinking of slope. Aspect, remember, is, or let me tell you now, I don't know if I should ask you to remember that now from past, but aspect is whether it's north or south facing. So in the northern hemisphere, if it's south facing, it's going to get more sun, and by definition, it's going to be a little bit warmer than the north facing slope. That's going to have a huge influence on your flora and fauna, and then of course on what your soil looks like. Your profile curvature, is it convex, concave? That's also going to have some kind of an influence. So when you're having a look at relief, I like this particular illustration over here. You're looking at the upslope and then the bottom land area over here. So you're looking at your depth of soil, your soil wetness, soil color, the type and expression of horizons, pH temperature, and the characteristic of the initial material. So if we have a look at the upslope, basically what's happened over time is that with for instance rainfall and things like that, you'll find that these soils, a lot of the finer materials may have been eroded or washed down from the upper slope to the lower slope over here. So typically you're going to find well-drained soils characterized by slightly coarser particle sizes. Okay, when you've got well-drained soils, your soil saturation is going to be intermittent because water is not going to stay here, it's going to run down the slope. Okay, not only above surface, but we're talking more beneath the surface. Either it's going to run down the slope or go down into the groundwater and then move across this way. So soil saturation is going to be intermittent, and because of that, the opportunity for soils to oxidize is much higher. There's a lot more oxygen in the soil pore spaces, and the result is that some of those metals in the soil, iron metals, for instance, are going to be oxidized and are going to be red. If you remember in the Soil Stories video, the guy was talking about he was talking about rusty soil, and that's exactly what it is. So you're looking at soil minerals like hematite, Fe2O3, and soil minerals like goethite. I can't remember that formula, but it's going to be a red or a yellow soil. So it's going to be a uniform. When you're talking about oxidized colors, you're talking about reds and yellows. What happens as you go down the slope is that you're going to have some oxidized colors, but you're going to have these mottled grays. So there's going to be, you're going to have the moderately well-drained soils, but what's going to happen is there are going to be some patches that stay wet all the time. And because they stay wet all the time, you're not going to have that opportunity for oxidation. In fact, these soils, as part of the metals in those soils will become reduced. When they become reduced, they lose that color, and you get a gray color or what we also know as glaying. So I'm going to write that here. We get what is known as a glay. That's a soil term. So we get a glaying color, and that's usually a sign of reduction in the soil. And so it starts out with mottling, and you literally get these mottles, these little patches. If you dig a hole deep enough, you'll find these little mottles of gray color in what might be a red or a yellow soil. And then by the time you get into the poorly drained soils, before you get to the very poorly drained, so this might be next to the river or something like that, what you find is most of the soil is gray or glay, and the only mottling that you find of the red colors is going to be the mottling around soil roots or soil root channels. Again, that's not that difficult to see, and I think if you go back to Soil Stories where Dennis DeFrancesco walks with us, I think that was the second chapter, you'll see some of those little mottles. And then finally, once you get into sort of very much the riverbeds or where it's permanently wet, your soils are dark and peaty, and you're going to have mainly blue and gray mottles all the time. So in that poorly drained soil, the rain soil, for instance, is one of them. It'll always be gray. It's because it's in a low-lying area, it's depressed. One of the other things, again, is you're going to find that as you go down slope, we talked about it, but over here, when you get down here, a lot of your soils the particle size distribution is much smaller, so you have smaller particle size. So color is going to tell you a huge amount, and so relief is going to inform of your color. It's unlikely that you would find a gray soil on top of the slope. You may have an isolated wetland for some or other reason, but it's unlikely that you're ever going to find a soil like that. Organisms are going to be plants and animals, and of course we also include microorganisms in that. We're also talking about human beings, but we're going to discuss human beings later. In fact, this whole thing of klort, I like to call it klopf. That human factor is way more important than perhaps sometimes the theoretical soil science or the pedologists make it out to be. But so in this case, this slide's telling us that humans are part of that. So basically, plants and animals are going to, and microorganisms are going to influence your soils in a huge way. Perhaps one of the most obvious looks at soil and the influences of plants on soil is looking at forested soils versus grassland soils. And this kind of seems a little bit counterintuitive, but it turns out that there's a lot more below ground biomass in grassland soil. So if you go to your prairies, you're going to find a whole bunch more biomass or organic material below ground or in the soil profile than you would in our forested soils. And why is that? Well, the grass roots are very much finer, and they do penetrate quite deep as well, but they're very fine, and once the grass dies, those grass roots actually die and begin to decay, and with that decaying process, they become they're dead, but then they become organic material. In the forested soils, often, the roots that go down very deep are going to be your tap roots, but it's large and it's fairly concentrated in one area. And you'll find your organic material really only concentrated on the top 4 to 6 inches, whereas in the grassland soil, some of those prairie soils might have 6 to 8 foot and more of very, very deep organic material in that, what is known as the topsoil, and we'll talk about that later, or what is known as the A horizon. So your above ground biomass in forested areas, like in the eastern part of the country, there's a lot more above ground biomass than below ground, whereas in the prairie soils you're going to find there's a lot more organic matter. Typical numbers over here we'll find in an undisturbed soil in the eastern part, forested soil, maybe 2 to 3%. In the grasslands, in the prairie soils, you're going to find 5, 6, 7% of soil. Exceptions, we have Carolina bays around here, and the Carolina bays might have up to 20 or 30% soils. Those are histic or organic soils. So organisms play a huge part in what's happening in soils. One example is the earthworm. Interestingly enough, of course, the earthworm is not native to the United States, but earthworms do form burrows. They do create pathways for air and water to come down. They have mucus-like secretions that line this, what is known as the drillosphere, the holes in the holes that they dig, and these are full of microbial activities. Plant roots, there is a zone about 3 millimeters around each plant root called the rhizosphere, and the rhizosphere organically is about 1,000 times more active than the zone outside of the rhizosphere. Now, why are organisms important? We haven't talked about microorganisms, but we've got things like bacteria, fungi, protozoans, nematodes, and things called actinomycetes, and we talked about that a little bit. But the big thing here, the take home right now for you just to keep in the back of your head, is that there's up to about 2 tons per acre of soil microbes. Never mind the macroorganisms and the mesoorganisms. 2 tons of soil microbes in the top 4 to 6 inches of a healthy soil. And those microbes are responsible for that 90% of soil function that we talked a little bit about in soil stories as well. Really important, and possibly in classic pedology not, they say that it's important, but it's perhaps not well explored, and we'd like to explore that as well. Time's another thing that is going to influence your soil. If you have a young soil, it's recently deposited soils, or recently exposed, it might be a rock in the Atlantic Ocean or something. Time has not had been able to act on that soil. So as time moves on, it's going to be able to weather the rock. Organic, the vegetation and the animals are going to be able to act on it. You're going to have the separation of the soil into different layers. You're going to have clay accumulation. You're going to have more weathered material in that. So time is another part of that. So the 5 soil formation factors, so it's parent material, climate, relief, organisms, and then time. And then, of course, we haven't really covered humans, but that will come later. Humans are a huge part of it. So remember that acronym, CLORPT, and that's basically the 5 or 6 soil formation factors, if you will. We'll talk very quickly about the 4 basic processes of soil formation. Now, if you look at Conker and Franzmeier, you'll see a whole bunch of things like physical and chemical wearing, weathering, leaching, accumulation of organic matter, clay movement, oxidation, reduction, and things like that. And so they have adequate explanations for those things in that. But there are basically 4 processes of soil formation that I want to show you. Is just this whole idea is transformation. So transformation really encompasses things like weathering of those primary materials, and they become clays or hydrous oxides. For instance, oxides might go from an oxidized form and get into, for instance, the soil might end up in a low-lying area, get very wet. Well, it'll go from oxidized state to a reduced state, go from red or yellow to gray or blue. You also have what is known as humification of organic matter. As organic matter breaks down more and more and more, it becomes more complex, and you have something called humus that forms, and it's in the soil environment. It's very difficult to break down, and that kind of almost becomes like a sponge, and sort of very, very high surface area becomes a location for a lot of your soil moisture to be stored, but also a location for many of your soil organisms, microorganisms, to live. We also have translocation, so that's within the soil profile. So, for instance, one of the things that you'll find is that you'll have an accumulation of clay not in your top or A horizon. Your clay will actually move down 6-12 inches and more into what is often known as a B horizon. So over time, water is going to wash those clays down into that next layer. Nutrients are also washed down, maybe not out, but maybe washed down the soil. And then so we're just looking at a translocation of a particular thing like a chemical or a clay within that soil profile. We also have things called additions. For instance, if you look at the additions, we cannot overestimate the influence of photosynthesis. And so plants are going to fix carbon, and that carbon is going to become part of that plant's body, and eventually when that plant dies, that carbon then becomes incorporated into the soil. So that is one of the major additions we need to remember. The other one is nitrogen. Nitrogen usually comes when you find nitrogen fixing bacteria symbiotically working with legumes, for instance, and that also then becomes an addition into the soil. Those things then break down eventually and become organic matter. But we also have sediments that might be washed down. Remember, we talked about alluvial or aeolian additions of sand, or maybe colluvium if this is at the bottom of a slope and you have stuff that gets washed down from upslope. So what else do we have? We've talked about transformation. Okay, we've got losses. I guess the classic loss are down here. Obviously, water is going to work through that soil profile and go into the groundwater system, and so water will carry with it a lot of ions. The classic ion that gets carried along is the nitrate ion. It's very, very, very soluble, and it's going to go where the water goes. So you'll often find losses from that, but you also have losses of water from the soil profile through evapotranspiration, which is a natural thing. There is a process called denitrification. When we look at the nitrogen cycle, we'll look at a little bit at that a little bit more. But denitrification will happen where nitrogen, for instance, or where soils are very wet, and the nitrogen actually ends up turning into nitrous oxide or it starts out as a nitrate, turns into a nitrous oxide, and then ends up as nitrogen into the atmosphere. And then, of course, we have erosion of our sediments. That's another huge loss, and often, or most typically, associated with man. Okay, so the discipline of pedology, if you talk about soil scientists, you're really talking about pedologists, and these are the guys. The discipline of soil science is really their job over the last 100 years has been to look at the description and interpretation of soil profiles and soil bodies, and then also to map soils on the soil surface. In the States, the Soil Survey has been going for, I can't remember exactly how many years, but at least 100 or 110, and we have essentially mapped the majority of the United States where we know all of those soils. Now, it's not always 100% accurate, but it's a pretty good body of work that the USDA has done over there. When we describe soils, we obviously can't look at the whole landscape and say, well, oh, you know, I can see underneath that. So that's very difficult. You know, part of soils, part of the reason why we misunderstand soils is we're not able to look underneath. So we've got a landscape, and then we've got something. What we do is we take from the landscape a polypedon or a soil individual. So this is a part of the landscape that is similar, and where we would expect the soil to be similar in that part of the landscape. That might be an area of 2 to 3 acres or more, 2 to 3 acres to maybe 20 acres in this part of the world. And when we look at that, we want to sample that polypedon. We can't look under every part of that polypedon. We'd look at that relief, and we would then sample what would be common to the relief and also common to the vegetation, and say, well, what does that look like? We'd either use a soil auger, or we would actually dig. You can see the soil pit over here. You can see these happy soil scientists. I don't know, I think they're probably from Clemson, digging around in the soil. But that is just a sample of the area around. But usually, if you know your relief, you know your vegetation, you're able then to infer what kind of soil series you've got going here. And soil series, or naming our soils, soil taxonomy, will be, I think, in the next lecture after soil profiles. So you're looking at a pedon as a sample of your polypedon which sits in your landscape. And when you're in the field, you're looking at things like a lot of it is subjective, but I'm going to skip this slide for the moment. You're looking at location, where you are, latitude and longitude, and that matters if you are in Florida versus if you are in Minnesota. You're also looking at your slopes, your relief. You're looking for your elevations. It's going to matter if you're on the coastal plain or if you're up in the Blue Ridge. And your aspect, the direction that the slope faces, and then what your vegetation looks like. Is it, a meadow? Is it prairie? Is it a forested woodland? So those are important parts before you actually start looking underneath the soil. Land use might also be part of that. And then once you start looking at the soil itself, you're looking at things like texture, color, structure, concentrations of different parts of those. In terms of color, is there mottling or is it uniform? What's the consistency? And that consistency really relates back to color, to structure and texture. Do you have roots Are there big pore spaces, or is it all compacted? And reaction, it usually is kind of a soil scientist term for pH. And so those are things that when we go out to in our field prac, we'll be looking at all of those different things. I don't know if it's going to be at City Roots or over at my place. I've got a garden, and we might look at it there. So I think I'm going to stop there right now, and then the next talk we'll talk about soil profiles and horizons.